It's a great pleasure for me to introduce you Professor Malcolm Fridlund. Malcolm is currently here as a visitor of the Fundación Jesús Serra, which invites every year, where we get every year one or two very senior scientists to ISC for stays of about 2 months, 2 to 3 months. I've known him for a long time as we have worked together in the Korot mission. This was at a time when Malcolm was still at ESTEC, where he was all his professional life, or very most of his professional life. He got a PhD at Stockholm University, and this is the country he is from. And he stayed at ESTEC until 2013, where he was a staff scientist responsible or supervising scientifically several missions, among them Korot, of course, the Darwin mission, and later also the Plato mission. Since he retired from ESA, ESTEC, he has been a guest professor at Berlin and at Heidelberg University, and also he is a permanent professor at Leiden University and at Chalmers Universities in Uppsala in Sweden. And there he recently got a major grant to set up an exoplanet research group for the next 5 or 6 years, where they will especially prepare for work for the CHEOPS and for the Plato missions. So he will tell us about his great experiences.
Yeah, okay. Thank you very much for that introduction. It suddenly dawned on me that I actually didn't do as many people go around different places when I was a graduate student and then became a PhD and did my postdocs. I went to my first postdoc place basically, and I was hired 8 months later, and then I stayed there for 25 years. But I'm doing it now instead. Since I retired from ESA, I've been hopping around like the worst postdoc you can imagine. I've never stayed more than 1 year in a place. But now I have this thing at Uppsala and in Leiden, so I'll go back and forth between those places. Now, it was never the intention for me when I started out in this business. I did my PhD in star formation, and what I really wanted to study originally was stellar physics. But they didn't allow me to do stellar physics because in the 1970s, late 70s, early 80s, it was considered that all stellar physics had already been done, so there was no work to be done. So star formation was the thing. I got a PhD in star formation. Luckily enough, I was hired by ESA, and the first missions I started to look at were dealing with actually with exoplanetology. They gave it to the youngest guy because in those days, we're now talking way before the first exoplanet was discovered, several years before. And of course, that meant that the youngest guy got to do this not really serious stuff and play around with it. And then I did that for 25 years, more or less. So today I'm going to talk a little bit about astrobiology from space. It will be partly a historical thing, really telling you why it should be done from space to a certain extent and why we did it or wanted to do it from space. And then I'm going to tell you a little bit about how I see things as looking to take place in the next foreseeable time for future when it comes to actually this very strange science called astrobiology, where we now have had it for, in certain aspects, very long time. And still, we're only dealing with one case. So, okay. Now let's see. Of course, this is all formulated on these big questions, as Martin Rees in Cambridge have formulated it. And for instance, what is the uniqueness of our own Earth? Is this the only kind of planet like this, or are there other Earth-like planets? We didn't know it, and we still don't really know it. Here's another one of these questions. Are we, as life forms, I mean, I'm lumping together not only the people in here in this room, everybody else on this planet, but also every living thing on this planet. And I'm even making a kind of excuses for viruses, because if you ask biologists and you get 100 of them together, you will find that about 60% will say that viruses are not alive, and 40% will now say that, yeah, maybe they are alive after all. So are we alone on this planet, or is there any more life out there? And what is our past? Because we know very little about it, actually. I'll get into that a little bit more. And what is our future? The formation of planets and how they evolve, that sort of thing. Now, there are three further important questions that come into this bit, which are very central to astrobiology. One is, what is life? Is a virus alive? I mean, life is actually going against the second law of thermodynamics. You're actually taking unorganized movement and making it very organized, which means that you have to unorganize some other movement. And I tell my students that actually just a matter of you being born has actually made the sun less organized. So it's sort of a kind of impact on how we are connected with the universe. When did life begin on the Earth? That's still a very open issue. And how did it arise on the Earth? That's also something that nobody really knows. Where, when, where? Well, just during my career, since I was a student, I've heard that it actually came out of these tidal pools, and therefore you need an oversized moon in order to have life on a planet. That it comes from black smokers on the bottom of the ocean. That it comes from, now the latest thing is tens of kilometers down into the mantle of the Earth, etc., and that's where it arises. I'm not talking so much about biology today as such, Earth-type biology, but one of the things in this context is, of course, that all the evidence for how life arose on the Earth are very indicative of that you need mutually exclusive environments taking place at the same time. You need a very hot area at the same time as a very cold area with high pressure and low pressure, and chemicals that are very hostile to each other, chemicals that have very long lifetimes, and those that have very short lifetimes. So you need to have all of this taking place at the same time in order to create life as we know it. So there are lots of open issues in there. But I mean, people have been discussing this for a very long time by now. I mean, the first one who actually wrote down something that has come down through the history was Epicurus, who was living 300 years before Christ. I mean, it's 2,300 years ago when he said that there are innumerable worlds, some like ours and other different, but we must believe that there are living things on these worlds. I mean, the Greek scientific climate was very fertile and allowed for many hypotheses. And already at the time of Thales, they had also realized the philosophical impact of the answers to these kind of questions. I mean, just the fact that you find life on another planet somewhere outside of the Earth would have great impact on a lot of things on this Earth. But this seminar is too short to get into all of these things. Thales had a student called Anaximander, and he imagined that there was this kind of life was not based, or the world was not based on water, as they had said before, but there was this mystic element which was infinite. And from this infinite, of course, if the world came out of this infinite thing, then, of course, other worlds could also appear and disappear. He made no claims about other life, but he thought it very likely that other Earths existed. Democritus, who everybody knows about, was the man who said that you can divide everything down to the point where you have something very undivisible, and that is called atom, which is what it means. And since worlds appeared from random action of atoms, also life could appear from random actions of atoms, which led to this Epicurus and his idea. However, Aristotle, who became so famous and traveled down through the dark ages after the antique world fell, that he became so famous and his literature survived so much that he was known for hundreds of years as the scientist. He, of course, had an idea that was based on the four elements: earth, fire, water, air. The earth rested in the central place because fire jut upwards and therefore it has to sort of go out from here. Earth has fallen to the center. He thought the atomists were idiots. And he concluded that the Earth is in the center of the universe, everything else orbits it, we are unique, we can only be the only home for life. And based on all this wrong physics, this idea lasted for more than 2,000 years. The world must be unique. There cannot be several words, his own words. Now, we had to wait for the Copernican revolution when Enlightenment started to fight religion. And the antique knowledge which has been kept safe by the Islamic scholars and now resurfaced during the Renaissance in monasteries and libraries across Europe, there had been critical thought a little bit appearing for the few hundred years before the Renaissance, but it's around 1500 that everything starts approaching a kind of boiling point. So it's time for the Copernican revolution. He didn't really discuss life, but he changed a lot of things. He was really a kind of polymath, studying everything like some bright people could do in that time, and also working in different areas. He also made translations of ancient texts, everything from pornographic literature from Rome to old antique Greek scientific literature into modern texts. He probably chose, instead of Aristotle, Aristarchus' sun-centered model, that the universe was centered on the sun, based on the fact that it was simpler to trying to explain the retrograde motion on the sky of the planets, just by sort of thinking about it. He was a very poor observer. He noted in the catalogues that the stars nowadays were in the wrong positions when he compared it to the ancient tables, but he only made 21 observations himself, and he never saw the planet Mercury in his whole life. So that was not really what was common among stargazers in those days. So the birth and the belief in other worlds came a little bit back at this time. You had Epicurus with his old ideas, and now you have Giordano Bruno, who actually stated that there are countless suns and countless earths all rotating around their suns in exactly the same way as the 7 planets of our system. He's counting the moon as a planet. The countless worlds in the universe are no worse and no less inhabited than our Earth. He was burned at the stake in Rome, not actually for that, but for being actually more out of sync with the Catholic Church on dogma. But it didn't help that he had stated this. Now, not every bright person were as open as he was. Galileo thought that ideas about life somewhere else were false and damnable. And here things stood for a long time, but slowly but certainly new ideas that could be connected to astrobiology came into astronomy and other things. Kepler wrote a science fiction novel about a trip to the moon, where the moon is inhabited. William Herschel claimed that the planets and even the sun could be inhabited. And Percival Lowell, if we go all the way up to the 19th century, were convinced, together with many other people like Camille Flammarion in France and others, Schiaparelli, that Mars was inhabited. Lowell was wild with astrobiology. He built a huge observatory, private observatory in Flagstaff, Arizona, which still exists, with one of the largest telescopes in the world at the time that he paid for himself. He was rich. And he discovered an extensive network of canals across the surface of Mars, and interpreted these as the engineering triumph by an ancient race carrying water from the poles of a dying planet towards the equator regions. Now, he had creative eyesight. What he saw was actually this. I mean, if there are any channels on Mars, they are the Valle Marineris, which is so huge that the Grand Canyon could disappear in one of its small tributaries. And of course, that would have been a real engineering feat if it had been done by a race. Somehow, maybe the disappointment in the fact that there was no sort of real engineers on Mars, and scientists realized that Lovell was a little bit off with these things, made these things an intermission. There was a pause after 1915 or something like that for a rather long time. I know that when I was starting at ESTEC, and as I said in the beginning, I was given these astrobiological things to start looking at. At the time, it's hard to remember now, but at the time, it was considered not really serious. I mean, if you were a serious active scientist in your middle of your career, you did not go out and look for other planets, because that was sort of impossible, and therefore you were not serious if you put everything into there. But some people did, and that of course led to the discovery of all the exoplanets we have today and things like that. And there was something happening. During the 1980s, the European Space Agency arranged several conferences dedicated to interferometry in space. And now we're coming to the technology of actually looking for something. Because one of the scientific drivers for such technology, interferometry from space-based application platforms, that was identified was the direct detection of Earth-sized exoplanets. The ultimate goal would be the detection of biomarkers. And this was based on a series of papers that appeared in the mid-1980s. I'll get back to them in a few minutes. The required technology that they were talking about in the 80s, which was just before I started at ESA, was actually so well thought out, but a little bit far-fetched. So it was classified actually officially as a green dream in the ESA Horizon 2000 scientific plan, which was issued in 1985, and which we actually just flew the last missions of a couple of years ago, because that was Herschel, was part of that plan that originated then. But in that plan you had cornerstone missions, which were large space observatories. You had medium-sized missions, which were slightly smaller missions. But you also had green dreams. And the two green dreams that came out of that was gravitational wave observatories and optical interferometry from space. The first job I had at ESA was to be supporting the ESA lunar study, which was the report was published in 1992. And one of the things we looked into there was the actual deployment of interferometry in space, or on the moon even. And we saw that the technology was very rapid. So the report we had said that this is maybe coming soon. One has to remember one thing, that as late as this time in 1992, when you sat down and you were looking and contemplating what does worlds out there, which actually can host life and everything, look like, the word was that all of these systems, absolutely all of them, will look exactly like our solar system. And why was that? That's an interesting question, and it has more to do with philosophy, I would say. Because the reason for that, when you ask somebody, why should they look just like ours? Why don't they look any different? Was, well, there's nothing special with us. And that goes all the way back to the Copernican revolution and the Enlightenment fighting the dogma of the churches and the ideas that had come before, with other dogma that said that it went from we are special to there is nothing special. And of course that was based on the same evidence, which is a rather interesting idea about it. So what we were thinking about in those days when we were looking at these interferometers, and we did that, the goal was to find one Earth mass planet orbiting one AU around a G25 star of about an age of, well, a couple of billion years. That was sort of the design specification. So the advisory bodies that ESA has started to actually think in 1993 that maybe the time had come to address the issue of life on planets orbiting other stars. And at that time, no normal exoplanets had been confirmed. The only exoplanets we knew about were the ones found around pulsars, a handful of small planets, and they were considered to be, which they were very likely are, just formed out of the debris from a supernova explosion. So they are not really what we would call normal exoplanets in the context of what the Earth is like. Anyway, in spite of that, not having any planets, in 1993, when ESA issued a call for proposals that should address the issue of looking for planets around other stars, a number of proposals were received. And one of them was for something called Darwin, and it was proposed as a nulling interferometer. I'll get onto that in a few minutes. It was selected in 1995, just before the 51 PEG discovery, as one of 6 missions for an assessment and industrial phase A study. And that was the first ever of a space interferometer to be technically studied by industry and by a space agency. But the Americans were not far behind. Out of those 6 missions, one is Bepi Colombo and the other one is Gaia, which are now flying. So the question is, why did you have to go to space to answer these big questions? What was the sort of idea behind the whole thing about the issue by a space agency to address this issue about what life is and how it comes and so on? Well, we get back to this idea about we don't know how life was formed on this Earth, and that is because all evidence for how life arose on Earth has been destroyed through plate tectonics, volcanism, and the revamping of the Earth's surface. One can mention in this context that the first life that we think is life on the Earth, the stromatolites that has been found, which are kind of early bacterial mats, I'll get to them in a few minutes, come from 2 places, maybe 3 now, that they have found in different continents in the world, one in Australia, one in Greenland, one in South Africa. Neither one of these areas where you find these very old 3.7, 3.5, 3.7 giga-years, billion years old, are larger than the surface of this room. So, I mean, that's what exists from this period. The rest of the Earth is sort of recycled in extreme. Now, we could study other planets in the solar system in situ if we want to look for life out there. And of course, everybody goes to Mars and want to see original life, etc., etc. But if we're going to talk about life in the universe, does that really tell us something? I mean, if you look at life on Mars, it turns out there has been life on Mars, or there even is something left, but more likely fossils of some early, very simple organism or something like that, if there is anything there. And it is based just like life on the Earth. Doesn't tell you anything, because if you look at the area, it came out of the solar nebula, and it came out of a small dust grain out of the whole universe. So we don't know whether if this life is the same as us, or as it's something, if there is life elsewhere. So, of course, it would be fantastic. Don't misunderstand me, but it's very uncertain what it would mean in the context of the concept of life in the universe. So if we could search for a large number of systems outside ours and try to find out if life arose elsewhere, that would be very interesting, because you only need to find it in one place and you would know that the universe is full of it. Because we refuse to believe that if it only happened twice in the whole universe, it would happen next to each other independently. It would, if it's so rare, then it would really be sort of not found at all. Of course, Hollywood has the same ideas as everybody else. We don't know what life is, and when we try to really make it strange, it doesn't become that strange. The only difference with this guy is that he has the brain on the outside instead of the inside. He seems to have the same interest as every crook in history before anyway. So, what we know today about life is that all life on this planet is very probably related and goes back to a first cell that must have been existent somewhere around 4 giga-years ago, who is called Luca, last universal common ancestor in the business. He is sort of, that's some kind of original cell that every cell on this planet, including all of the myriad ones that we each consist of, and all the parts in us, are related to this. Other issues is that after Luca, no new life in the same process that started has taken place on this Earth. It's not so that life arises all the time and is beaten down by the life already here. It just doesn't happen. Nobody knows. I mean, no indication of it exists. And that is the interesting thing. Huh? So that's the opinion of them. The oldest fossils are probably these stromatolites that I talked about, which were simple prokaryotes, one cellular organism with no nucleus. 2 giga-years ago, cells with a nucleus evolved. We can find some kind of fossils from them, the eukaryotes. Maybe they were producing oxygen. That is Not really known, but there are some indications of it because you find iron oxides in layers from this, geological layers from this period, which are so big that they cannot have been formed in an abiotic way. At least that's the hypothesis. Multicellular life doesn't appear until about 650 million years ago. And the first signs that you find are sort of fossilized tracks of worm-like life, and how you went from that to that, nobody has any idea. Then, of course, we have the Cambrian explosion at 542 million years ago, which is found in the Burgess Shale in Canada, where suddenly, all the phyla that exist today on this Earth appear. All the kind of animal areas where you have spiders, scorpions, you name it, plus a whole bunch of things that does not exist today. Nobody knows why that happened just like that either. And this is sort of where you get organisms with shells and exoskeletons appearing, and that's why we can really find them, because of course they fossilize better than soft things. First vertebrates, 488 million years ago. Jawless fish are probably the first things that swim in the sea. So far everything is still in the sea. And then you get the plants on land about 420 million years ago. First frogs, first mammals appear just around the same time as the dinosaurs. First primates, end of the Cretaceous. Separating from our cousins the chimpanzees 6 million years ago. Homo erectus, who was a very smart guy because he actually moved all across the planet, existed 1 million years ago and lasted as long as maybe 143,000 years ago. He was a real smart guy. And of course then you have all the Neanderthalians, which actually disappeared just 40,000 years ago. Homo sapiens, which walked out of Africa 200,000 years ago, who learned how to build a radio 140 years ago and a laser 55 years ago. So this is why I have not started working for SETI when I retired, because I consider that to be a very long shot. I'm happy that they are doing it, and I think it's great that they are doing it, but I think their chances of actually seeing something in the galaxy is rather small, given the fact that radio exists in on a ratio of 140 years to 4.5 gigayears. So what did Darwin have to do with SETI? Darwin could not be designed to look for intelligent life, and it could not really be designed to look for highly evolved life. So the Darwin, and now I'm not talking about Charles Darwin, I'm talking about the project, science team recognized that life had existed on the Earth more than 3.5 gigayears, and all of these things here, you would really have to look for all of these concepts. So all of this came out of a bunch of papers by people like Ron Bracewell, Roger Angel, Nick Wolf, Toby Owen, who passed away just a few days ago, and Bernie Burke, really smart people who wrote a sequence of articles in Nature in the mid-1980s, where they actually were discussing telescope design, spectroscopic biomarkers, etc., and identify those. And based on this work, a bunch of French guys, Lecher, Schneider, Rouen, Jean-Marie Mariotti, and their co-workers in France produced to ESA a study of a nulling interferometric telescope that would be sensitive enough to detect oxygen, water, and CO2 in the Earth's atmosphere at a minimum of 10 parsecs. When this proposal was filled, there had not been discovered any single exoplanet in the galaxy. But these guys proposed to do this, and of course they set the limit to 10 parsecs because they said, okay, there has to be a planet around every star, and of course we are not special, so therefore there's going to be planets, and if there is a planet with the right conditions, there's going to be life on it. That was sort of the general hypothesis in those days. And ESA picked this up because we had studied it before and so on. We had done all of these workshops, conferences, technical studies before this, since the early 80s. And Darwin was also going to search for life because we want to understand ourselves, because we didn't know how life and so arose on the Earth. So you had to have something that sort of looked at these things. For instance, how fast did life arise on the Earth? that would mean that you would need to know how old the planet were if you looked at it and you saw signs of it. And if origin of life is a simple process, maybe it happened several times on the Earth. We don't know that. But you would know it if you find 10 planets like the Earth and you find life on at least one of them, then you would know that it is a relatively simple process. If you have to look for 1 million planets like the Earth before you find life somewhere, it's a rarer process. And if you never find it, it's indeed a very rare process. The governing principles for the origin of life on the Earth, in the solar system, and in the universe, you can answer that way, but maybe no other way. There was a very big conference at the Royal Society back in 2011, I think it was, in London. I was invited just to talk about ESA's missions. But there were most invited people were big guys like Nobel Prize winners. There were 5 of them there, and so on, and none of them could agree on a single thing. There was one Nobel Prize winner who claimed that life is a cosmic imperative, and that if you have the right substances, the right environment, then life must arise. And there were several people there who argued that totally the other way around. The chemical pathways leading to life are so improbable that it only happens once in 10 to the 136 years. And that would mean that since the universe is only about 10 to the 10 years, and it happened obviously once, that it's only happened here, and that's it. So, you sit there and you listen to these things, and you sort of, you think, okay, there is a simple way. We go and look. We just go and look. And if we don't find it, it's rare. If we find it, it's common. It's as simple as that, very binary. So I can't see why we don't do that. So we need to go and look somewhere else. And then, of course, an added plus if we do that is that we learn a lot of other things about life in general, and planets, and the universe. So biomarkers were considered, we were simple in those days when we started this, and this is not as simple any longer, but we figured that here you have 3 cases of terrestrial-like planets where we have good spectra, and of course based on these there is one with life on it, and we know that. So I don't see why we bother about Mars or Venus in any way, but maybe there were life there. You could imagine it. But you can clearly see that the spectra are different from them. Here you have oxygen in the form of ozone, and you have water. And here you have very little water, and all 3 have CO2. Now, CO2 is common molecule, so it's not very strange, and it comes out of the Earth because carbon and oxygen are 2 of the most common atoms in the universe. So if you have a hot planet and you have volcanoes, they are going to spew out CO2 and other substances like that. Oxygen, on the other hand, happens to be the most reactive. Actually, molecule O2 is the most reactive molecule in the universe. If you put it next to something, it will react with it. It will either form water, it will form CO, CO2, SiO2, etc., etc., etc. So, if you don't produce oxygen continuously through some dissociative energy demanding process, you will not have any free oxygen anywhere. You take away all the life on the Earth, including the one-cellular organisms, our friends, plankton and everything, and the oxygen on this planet disappears in a very short time. Less than 100,000 years, and it goes out. So the idea was with Darwin that we were going to look for a planet that was chemically out of equilibrium. And of course then with ozone and oxygen, but if we consider the fact that maybe oxygen is not forming until later in the history of life, you might want to look for methane, N2O, a few other reduced molecules, and so on. And this was, of course, hypothesis of people like Lederberg and Lovelock back in the 1960s, and Toby Owen in the 1980s. So the Darwin plan simplified looked like this. For each planet we found, we should analyze the reflected light to see if it had an atmosphere. Then we should look for liquid water, because that's relatively simple. Then we look for oxygen, a bit harder. And other signs of biological activity like methane, which is produced by this planet's animals. And then we exclude every other explanation, which is not maybe the most trivial thing to do. So that was the simple part of the Darwin study. When we started this thing, we spent the first year formulating these things, and we had been taught that a nulling interferometer would be the thing to use for this, because there were problems of really resolving a planet and everything like that, but we hadn't really realized how difficult that would be. It might even be the most difficult problem in astrophysics, because terrestrial planets are small and the whole star is much brighter. So if you want to sort of get the planet out of this, I mean, we were considering these things about transits in those days and analyzing atmospheres and things like that. And we came to the conclusion that this was totally impossible, because you need to loft a very big telescope up into space. Actually, it's the same thing now. I mean, you look at the James Webb telescope, which is going to try to do transit spectroscopy on exoplanets. They can do a very large super-Earth or a small Neptune, and they can do one during the whole mission, or maybe two, if they happen to be within 5 light years, or 7 to 10 light years, or something like that. And that's about what you will be able to do. And for doing the Earth, you need something like a 20-30 meter telescope in space. So we disregarded that at the time. The habitable zone where water flows is very close to the star, even for a system like ours. Of course, this is the good old thing where you sort of look at it, that you're looking for the firefly on the lighthouse, and you do it from the other side of the Atlantic. But what it really comes down to is the fact that the contrast in the infrared between the sun and the Earth is 10 to the 7, 10 to the 8. In the visual, it's more than 10 to the 9, more like 10 to the 10. So for each photon of the planet, you're actually receiving 10 billion in the visual and 100 million in the near infrared. The angular separation for the Earth-Sun at the 10 parsec is of course 0.1 arc-second. And if you consider the fact that we were looking for G2 stars, and within 10 parsecs there are 18 of them, then it's not that many targets to look for. And of course the spectrum from the Earth in the infrared, where the contrast is the best, actually where the Earth is maximum and the Sun is dropping, you get 1 photon per square meter per micron of bandwidth per second. So it takes a while to build up a very good spectrum that way. So we have dynamic range and resolution, and the infrared is of course advantages. So now we come to nulling interferometry, and the idea is brilliant, very simple. If you have a very bright star here and very close by, small angle, in this case 0.1 arc-second away, and you put in the right phase blocker between here, and you delay the light from one of the telescopes before you combine the two beams, you can turn out the light of the star and enhance the light of the planet. So it looked really nice concept, and this is as far as they got in the 80s. But we put this to the test and started to look into whether it was technically feasible. So first we had one company in France to look into this, Alcatel. And then we had another French company who did not get the contract to look into it. So they had the incentive of finding out that the first company had screwed up. And both came to the conclusion that it actually would work. I mean, you would get a transmission pattern that looks a little bit like this, or rather on your CCD detector, it would look like this. And the idea is that you put the star here, and then of course you make certain that the distance here is the right distance to the habitable zone, which you do by just moving the telescopes away from each other. And then you rotate the whole thing, and you can actually make a transmission pattern on the sky where you get the light from the planet passing through as you rotate and modulate it, and then you know where your signal is, and then you feed it through a spectrograph, and you write your paper, and you go to Stockholm and collect your Nobel Prize. Sounded incredibly simple, so this is the design that we came up with. And of course, why don't we have it up there already? I mean, I made a very good case for it just now. Well, It started in the middle of 1996. The start was delayed a little bit because we happened to drop the cluster satellites. They exploded. So we actually did not kick off the industrial study until 1997. So we did a concept and feasibility study. The report was presented in July 2000 in Paris. And at the time, we realized there was no way we could fly in 2009. So we were actually asking for a flight opportunity of 2014. And that would leave the field clear for Bepi Colombo and Gaia, who were to be launched in 2007 and 2009. So I actually had an email very long time before I lost it, which said from headquarters in Paris that said that I would work under the assumption that Darwin was cornerstone 8, the next cornerstone after Gaia. Darwin needed significant technical development, and it's little known fact that we actually spent about 30 million euros in technical research money between 2000 and 2005 to develop different things. One of the things was, for instance, free formation flying, which in the end was done by the Swedish Space Agency together with the German and the French one, with 2 satellites called Mango and Tango that are still up there, and which are doing that and have demonstrated it. So this technology is now flight qualified, as is the phase shifting and all of these other things that we were doing. There was also an intensive collaboration with the Americans at this time. We started about the same time, and for the first and so far only time since ever, we have worked in a 50-50 joint partnership between ESTEC and JPL, between ESA and NASA. We ran the studies together. The members of our science team were members of the US team and vice versa. And of course it did wonders for one's frequent flyer miles, but it was also a bit tiresome. But it worked very nice, and we came up with several designs. We had a European design, where we have them in triangular formation with the beam combiner satellite in the middle, and the Americans favored this. And then, of course, there were the guys for the Space Telescope Science Institute who wanted a 16-meter telescope and a coronagraph. And anyway, it was put into the science plan of the Cosmic Vision. So you can see the first would be an in-depth analysis of terrestrial planets, then understanding the conditions for star and planet formation and the origin of life, eventually image terrestrial planets. So we were already talking about that. And this is the proposal for the Darwin mission from the 2006. But times were changing. After 2005, both ESA and NASA decreased the money and effort put into Darwin. Somehow it was considered that the cost of a Darwin mission would be something like 4 times the cost of James Webb, and nobody wanted to take the responsibility for that. In the end, in 2007, it was not selected for L1, the first large mission, which is Athena nowadays. The technology feasibility mission that we had planned on was given instead to LISA, and that was because NASA intended to fly the LISA, the gravitational wave mission, in 2009. So the Pathfinder needed to fly in 2007. As we all know, it launched last year or the year before, and it's still up there now. We had a technology precursor experiment which became too expensive, so that stopped it. But the most important reason about Darwin sort of grinding to a halt was that we learned new things about exoplanets. Darwin was conceived when we expected that all exosystems would look like ours, and they don't. So far we haven't found a single system that looks exactly like ours. And until we know where our systems are, nobody is going to spend the money on building something that can do this direct spectroscopy of Darwin. On the other hand, there was a planet reported not too long ago around Proxima Centauri. Another planet has been reported around Alpha Centauri B. Both of these planets, Darwin would have made a spectrum with a signal to noise of 100 in about 5 minutes. So you would know whether there was an atmosphere and what it consisted of and everything, because they happen to be the most closest objects we have. So if there is something like that, it might be coming around anyway. Darwin was a project conceived in the days of big science. It was high risk, high yield, and now a more stepwise approach is suggested. we have to find out what's out there. Well, this is what Hans and I used to work on together, Corot, which actually was a very early precursor mission in this context. We found 40 confirmed planets. We have another 40 planets which are sort of confirmed in the American sense, i.e. we don't have radial velocity observations because the stars were too faint, but we have excluded all other opportunities. There is a large paper called the Mega Paper coming out quite soon about the final result of it. There are still 211 candidates that would need to be followed up. If the stars were not 16th magnitude, then you can't get the radial velocities because they all have if they all have planets, they are all small planets. It did major new discoveries in astroseismology, and Kepler we all know about. I mean, they're now sitting there with their fantastic results, 578 multi-planet systems as of 10 days ago, about 10 Earth or super-Earth planets in the habitable zone or potentially habitable zone around their target stars. We are looking for the future. We are going to get TESS, which is of course going to survey 30 to 100 times brighter than those surveyed by the Kepler or by Corot. They should be easier to characterize with follow-up observations, and most important is that TESS is designed with its spectral range coverage and everything to be a precursor for James Webb. They are designed to find transiting planets around nearby red dwarfs. We have Cheops, which is a similar thing, but it's not a survey mission. It's instead looking at details around planets, bright stars, very bright stars that are known to host exoplanets, and study them in detail with a transit way. James Webb is launching finally, and is going to do spectroscopy of Jupiters, Neptunes, and maybe the odd super-Earth if there happens to be one close by enough. And then we're waiting for Plato, which is doing its big difference, is that it's going to take what Kepler did and do it better, and it's also going to do the stellar physics of the stars by itself, so that we have the information about the stellar, not only the radius and the mass, but through astroseismology also the age. And of course, that will tell us more about what planets are out there. And we will understand more about the evolution toward habitability after that. I can skip this. I mean, it's a lot of things, including planets of all masses and sizes on various orbits and all types and ages, and doing this seismic characterization of the host stars. The important thing about that is that you will get in the future, as demonstrated by Kepler, a resolution in time of 250 million years instead of 2.5 billion years, which is stellar physics, what stellar physics can do from spectroscopy. So after we have all of that, well, in 10 to 12 years, we should know how many terrestrial planets there are out there, really, and how many systems looking like our own. Could be few, or it could be many. It couldn't be that many, because out of the stars we have looked at so far, the brightest stars in the skies, we have quite a number where we don't know that there isn't any system like ours, because there happens to sit a big Jupiter-like planet in the habitable zone. So there is no place for it. But who knows? There may be moons. We will also have the first good spectra of giant exoplanets, and possibly of a few super-Earths. And we will know roughly from the Plato mission the internal compositions of these planets that we have found. So then, maybe then, it will be time for doing something like this, and do this direct characterization, and go through with detailed spectroscopy when we know where they are. Thank you very much.
Thank you, Malcolm. Are there any questions?
How robust are the biomarkers, in the sense that in a couple of occasions biomarkers has shown positive results in some sense? For instance, in Mars, methane was discovered and also in the Vikings, some results also look like biomarkers, but they were discredited as geological effects.
I would say that they are not robust at all. They were robust. They were very robust in the 90s. You could swear by them, and that was very comforting when we were designing things. But then, of course, in the first decade of this millennium, people started to look into these things because we were working on it, and they started to question them. So they are not very robust at all. I mean, of course, if you have a heap of oxygen in your atmosphere, or very much methane, and you can say for certain that this is definitely not geological, because you can see the geological features. I mean, you have so much methane that you would need to have volcanic vents that were visible. Then of course, there is something going on. But otherwise, no, you can't really say anything. There are even chemical reactions. For instance, you can design a planet in your models where you have just exactly the right gravitational pull, so that the water vapor goes up onto the top of the atmosphere, where the water is dissociated and the hydrogen goes away because it has escape velocity, and the oxygen stays. And then it sits there, and under the ultraviolet it forms ozone, and you get a nice Darwin-like signature. But there is no life on this planet, there's only water. So I mean, people tend to talk about water as being a necessary prerequisite for life. It very likely is a necessary prerequisite for life, but it doesn't mean that life forms just because there is water.
Any other?
You hadn't mentioned panspermia as the possibility for the origin of life on Earth. It's because it's completely out of, I don't know, it's no longer in fashion, or it's too exotic, or...
Well,
I mean,
no, not really. I mean, there is this group of people, and I think the most known member now that Fred Hoyle is dead is Simon Conway Morris, an evolutionary biologist in Cambridge who did lots of work on the Burgess Shale and things like that. He is one of the guys who have calculated these things and thinks that, together with the mathematician Roger Penrose, think that life is so unlikely that it could only have happened once. But that doesn't mean that it was here it happened, but that panspermia has spread it all across the universe. But that, of course, would need to, as Fred Hoyle used to say, that the universe is older than we think it is, and there are lots of these. I say again, let's go and have a look. I mean, if panspermia works, then we will find it, life everywhere.
Yeah, but if I understand, part of the business is that the life is created in comets, so tiny little bodies which are, you know, if it is hard for us to see Earth-like planets, I mean, to study individual comets from...
That's true, but the idea is that even small life sort of multiplies. I mean, you look at the... I'm not an expert in this area, so I can't really tell you what the evidence is, but even the pre-karyotes apparently cover the whole Earth. And you can say that from, for instance, these banded iron formations that you find all across the Earth, which are 3 gigayears or more, 3.5 gigayears old, and which indicate that something was alive on this planet producing so much oxygen that essentially all the free iron that existed on this planet rusted and formed iron oxides. So you would be able to see these things, but I would say that that's another of the reasons why I don't feel too unhappy about not flying something like Darwin today. It was designed to look at the 1,000 closest stars. The chances of finding a solar system that looks like ours around the 1,000 closest stars is very low, apparently, because the real estate is taken up by other systems, and the biomarkers are not any longer robust. The good news is that actually there are lots of people now in other disciplines than astrophysics working on this, and they are really producing. I mean, lots of modeling work is being done about the different biomarkers that you could expect. But we need to find the real estate. We need to find some good planet to look at.
mentioned at the beginning that there is no clear evidence that life is appearing continuously on Earth.
That's what they claim, the biologists, yeah.
Yeah, but could you expand a little bit more on that? I mean,
well, I don't know that much on it, but I know that there is absolutely no evidence that any new life has formed on this planet for the last at least 3.5 billion years since this Luca thing, because you can do this kind of DNA analysis and RNA analysis and see that everything on this planet is related.
Yeah, I mean, I was thinking that this was your answer, but I mean, unless when life forms and reproduce, it's created using the same rules. No? I mean, then we should not be able to see that happen.
Yes. Well, this is of course something, I mean, that is debated. I know about a couple of guys in the States, rather young guys, who are actually looking for life that's formed in a different way than our life. I mean, that is not based on the same principles, but they don't really know what to look for. So they are sort of trying to see things that replicate and do these things. I mean, to a certain extent, you can say that a computer virus is alive. I mean, it follows certain of the rules that you have for how you define life, but I wouldn't call it alive. It's sort of it's a very difficult issue.
It's getting a bit late. Okay, so we have 3 more questions.
Thanks for the talk. More of an engineering question. I don't know if you can answer it. I heard of another idea, another project with space interferometer that was dropped because it was concluded that you cannot hold the light beam coherent. And it was like, oh, you have like 5 or 6 elements that are floating in space on a big distance, and you cannot keep track of their velocity and hold them stable. And there is even a thing like solar light pressure that we know can even turn the Kepler telescope and even things like this influence. So how much would you say is this of an issue, and is this really an unbearable hindrance?
Yeah, it was not really a problem because at the beginning everybody thinks, including ourselves, you think that you launch an interferometer in space, and that means that you need to have spacecraft together to this enormous precision, which you don't have to. What you do is that you send the beams from each telescope. They are each collecting the light, and then you do pupil addition of it inside the beam combiner. So this satellite you have, which is a small area where you have all the light control systems sitting inside this thing. And if that didn't work, then LISA Pathfinder up there would have not worked at all, because they have 3 orders of magnitude higher requirements than what Darwin had. So in principle, one of the good reasons about going to the 10 micron band is that it relaxes the precision that you need to have. You need a lambda over 10 to lambda over 100 inside the system, and that's not really hard to do these days. And you can do it with many different technologies. We had 3 of them that we developed. So the beam combination, for instance, is nowadays done on a chip at 10 microns. So this is not really a problem.
Can you just tell a number, like the distance between the elements, like the diameter of the interferometer?
The diameter of the interferometer, well, the closest I think it goes down to 20-30 meters, and we were actually basically trying to look at least 500 meters in diameter to go down to distant stars and even longer. I mean, in principle, there is no limit to it as long as you can control it. And that's the same thing, you know, you've heard about these occulters. They have another system where you, instead of having an interferometer, you're flying an occulting disk 50,000 kilometers away from your telescope. And you shield away the stellar light that way. And you have to keep that one in position, much higher position than what you do with the interferometric telescopes.
Okay, thank you. So shall we take a very last question by Arturo?
One amazing thing about life on Earth is reality.
Yes.
So do you think this is a must for life, or is an exception, or?
I have no idea. I mean, I've heard people have said that either it is that, or it is just that life happened to start out left-handed on the Earth, and then it killed every right-handed thing that were competing with it. The first things. Nobody knows for certain. What I find interesting is that actually in cosmos, you find a kind of higher rate of the same chirality as we have on the Earth. And there is a very interesting aspect. This is just something. This is not anything I know. It's not my field or anything. It's just an idea that came into my head when I learned about these things. There is some indications in the isotopical ratios in the solar system that the solar nebula, when it was cohering into the planets, was exposed to not one but two supernova that had to be at least 0.9 light years away for not dispersing the nebula, and not more than 1.3 light years away in order to give the isotopical ratios we find in the solar system. And they had to detonate within 1 million years, and they had to be at these distances, and there had to be two of them, which would say, normally to astronomers it says we were formed in the core of a cluster somewhere with like Orion, but I would also say that that could play havoc with things like chirality and stuff like that, particularly if you have formed your amino acids and stuff like that in space, and they end up on comets or something like that, and you basically make them left-handed by the polarized radiation from the leftovers from the supernova explosion, the neutron stars that you form. But I mean, that's just hand-waving, just an idea. I don't even know how strong the evidence is for two supernova. One supernova, it's definitely so, but... Okay, yeah. Well, you know that better than me, but at least the supernova could do something funny with the chirality, because the radiation from it is polarized.
Okay, thank you very much.